Welcome back to Physics 151 Online. Now that we know how to calculate the work done by a force on an object as it moves, we will distinguish between two different types of forces and show that for one of them we can define a new term called the potential energy, and that will greatly assist us in analyzing the motion of objects when they are subject to different kinds of forces. So, this special kind of force is called a conservative force, and forces that have this property do work on objects that does not depend on the path that the object travels to get from the initial point to the final point. In other words, the work done is independent of the specific path and only depends on the starting point and the ending point. So in this schematic, imagine that there's a force F acting on an object moving from position 1 to position 2, and of course there's an infinite number of pathways, but let's just imagine 3 of them. So that object can either travel along path A, or path B, or the direct path C. And so some forces have the property that the work done to get from point 1 to point 2 is the same along any path, and therefore only depends on the initial and the final location. But how do we know that such forces exist, and what are some examples of them? Well, we can do some very simple example calculations to show that the work done by certain kinds of forces does not depend on the path that they travel. And gravitation is one of these forces. Let's look at the work done by gravity on an object when it moves near the Earth's surface. Consider two paths that an object could take as it slides from the top to the bottom of an incline to go from point 1 to point 3. There's of course the direct path, which would go directly from 1 to 3, but then there's an indirect path where it might move horizontally from 1 to 2 and then vertically from position 2 to position 3. And so if the incline has a height h and an angle theta, we can calculate the work done along these two paths and show that they're the same. So first of all, let's take path 1, 2, 3, where it first goes horizontally and then vertically. So the work done along that path is the sum of two terms, and work is always the dot product of the force and the displacement. So to find the work along the segment that goes from 1 to 2, we look at the force, and the only force acting on that object would be the force of gravity, and the displacement S12 is along the x direction, which we'll call with unit vectors the I hat direction. That distance as it goes from 1 to 2 can be written in terms of the height of the incline and the angle. The tangent of that angle is equal to the height h divided by that distance from 1 to 2. So that distance from 1 to 2 is actually h over the tangent of the angle. And so now with those two vectors, we take their dot product, but notice those two vectors are 90 degrees apart. And so the work done by the force, the gravitational force, when we go from position 1 to position 2 is going to be 0. Then we can look at the path from 2 to 3. As the object moves from 2 to 3 now vertically, the gravitational force is minus mg j hat, and the displacement is minus h j hat. Those are parallel to each other, and so we can see that their dot product will not be 0. So work 1-2 is the dot product of the gravitational force and displacement S12, that's 0. Work 2-3 is the dot product of the gravitational force and the displacement S23. Those are parallel to each other, and so the work done is mgh. The minus signs, of course, cancel because the two vectors are in the same direction. So therefore the work done as we go from position 1 to 2 and then 2 to 3 is mg times the height h. Now let's look at the same object but calculate the work done on it as it moves along the incline from position 1 to position 3 directly in a straight line path. So to do that, we need the gravitational force again, and then we need to write down an expression for the vector that takes it from 1 to 3. And again, we can just express that in unit vector notation as having one component along the I hat direction and then one component along j hat, and so the vector S13 would be given by the sum of these two terms. So we can take the dot product of the gravitational force dotted into S13, and we just do it component by component. So when the j hat dot I hat term will be 0. That's the first term because they're 90 degrees apart. The j hat dot j hat term is equal to 1, so we get minus mg times minus h, or mgh, and therefore we get the same answer. So W13 is the same as W12 plus W23. We've only considered two specific paths, but in fact you can show for the gravitational force, no matter what path an object takes to get from its initial to its final location, the work done by gravity only depends on those two positions and not the path. And this shows, according to our definition, that gravitation is a conservative force. Now, can you think of a force that we've discussed in class that's not conservative, where we can't just assume that the work done by that force depends on just the initial and the final position? And I think if you think about it for a while, you can find one of them for sure that does not have that property. But let's look at the definition that we can make of this new quantity, the potential energy function, and we'll give the symbol U for the potential energy. And we can only define the potential energy for a conservative force like gravitation. That's what's special about conservative forces. So the potential energy function expresses the energy change that's associated with the motion of an object between 2 points, and it only depends on the initial and the final position. So the change in potential energy for the object is equal to its final minus its initial potential energy as it moves from one point to another, and the definition of this is that it's equal to minus the work done by the conservative force whose potential energy we're calculating. We'll see the reason for the minus sign in just a minute, but if we just accept this definition then this potential energy change is minus the integral of f dot ds, because remember, the work done by any force is just the integral f dot ds from its initial position to its final position. So let's calculate what this is for an object that's lifted from the Earth's surface, where it starts, to a final height h. So the vector displacement is hj hat. Of course, the gravitational force is minus mg j hat. So if we use this definition, delta U is U minus U0, which is, for this case, since the gravitational force is constant, we can pull it outside the integral sign and we just get minus F dot S, the displacement vector. So the F force dotted into S, since they're 180 degrees apart from one another, the dot product is going to give us a minus sign. And so it'll be minus negative mg times h. So minus negative mgh gives us mgh. And that tells us that the object, when we raise it from the Earth's surface a height h, increases in potential energy by this amount, mgh. And therefore, if we just solve for u, and now we'll give it the subscript g to indicate that this is the potential energy due to the gravitational force, it's equal to its initial potential energy plus mgh. And notice in problems like this that u0 is an arbitrary value that simply defines the zero of potential energy. We can choose that position where we're going to call the potential energy to be 0 anywhere we want that's convenient for a particular problem. Often we choose the zero of potential energy to be at the Earth's surface, but not always, and the choice is up to us. Nevertheless, we now see for gravitation the potential energy is mgh, and for this reason you see it only depends on the position of the object. It only depends on its height, and so sometimes potential energy is called the energy of position. You also can see why we introduced the minus sign into the definition when we define potential energy change, because if an object is raised from the Earth's surface to a certain height and then released, it falls down, and so it generates kinetic energy as it falls. It increases in its speed, and so it makes sense if we think of an energy of position, that an object would have a greater potential energy when it's raised up a distance h than it had where it started down on the Earth's surface. Without that minus sign in the definition, we would have gotten a potential energy that would be negative instead of positive. So that minus sign is important. Now let's calculate the potential energy due to another kind of force that turns out to be a conservative force, and that is the force that a spring exerts when it's either compressed or when it's stretched. We haven't talked about this in class so far, but there's a very simple relationship that tells us what the force is exerted by a spring on an object it's connected to when the object undergoes a displacement x away from the equilibrium position. The equilibrium position where x is equal to 0, that would be where the spring is at its regular length. It's neither stretched nor compressed. So that equation is called Hooke's law, after Robert Hooke, who first wrote this down, and it tells us that the force increases linearly with the displacement x away from the equilibrium position, and that the direction is opposite to the sign of x. So if we stretch the spring like the diagram indicates, then the force is in the negative x direction. If we were to compress the spring so that the x displacement would be negative, then the force would be in the positive x direction. So using this equation, which is Hooke's law, it's easy to show that the work that a spring force does only depends on the initial and the final position. So if we calculate the potential energy change, it's minus the work done by the spring, and so minus the integral of the force of the spring dot ds from the initial to the final position. And we're trying to do this starting at the equilibrium position, moving out to a displacement x. So we now change the expression for the force, because we now know the force is acting only along the x direction. So the dot product f times ds, or dotted d into ds, would just give us f sub x times dx. So we substitute in for f sub x. We know that that's minus kx. We plug it in here, the minus signs go away. The k is the so-called spring constant, which is just a proportionality constant that tells us how stiff the spring is. It comes outside the integral, and then this integral of x prime dx prime from 0 to x is very simple. It's just going to give us x squared over 2. So the potential energy change that the spring has when it's stretched from x equals 0 to its final position or displacement x is 1/2 kx squared. And normally in spring problems we make the choice that the potential energy at the equilibrium position where x is equal to 0 goes to 0. So that means we would let this constant u0 be equal to 0, and that would give us the potential energy expression for a spring. 1/2 times kx squared. And notice that if x is equal to 0, the potential energy is equal to 0, which makes sense. If the spring is at its equilibrium position, it's not going to move at all. Now, having defined potential energy for the two cases of a gravitational force and a spring force, we can now show how the modern day expression for conservation of energy comes about. Since we now have divided up all forces into two different kinds, those that are conservative and those that aren't, which by implication means that those are non-conservative forces, we can write down the net work done on any object as it moves from an initial to a final position as equal to the work done by the forces that are conservative forces and the work done by non-conservative forces. And by now you probably thought of this before, but an example of a non-conservative force is friction, because that could be a force where the work that it does is going to depend very much on the path that the object travels as it slides, let's say, across the surface of a table. So the work energy theorem says the net work is the difference in kinetic energy, and so we just expand this expression for the net work to include these two terms: the work done by all the conservative forces and then the work done by all the non-conservative forces. So what we now know is that the work done by conservative forces through the definition of potential energy difference can be written as minus the change in potential energy. And if you just go back a couple of slides, you'll see that. So delta is always final minus initial. The minus sign turns this into U initial minus U final. So let's just make that substitution into the expression in the work energy theorem for the work done by conservative forces. So that means that this becomes U initial minus U final plus the work done by non-conservative forces equals K final minus K initial. And if we rearrange this and put all of the initial terms on one side and all of the final terms on the other side, we have the expression known as the conservation of energy. So it tells us that the initial kinetic energy added to the initial potential energy plus any work done by non-conservative forces that are involved equals the sum of the final kinetic and potential energies. If you have a case where there are no non-conservative forces acting, where there's no friction and no other forces, then this would tell us that the sum of the kinetic and potential energies would be the same initial as they are final when an object moves from one place to another. And for that reason, a lot of textbooks define the sum of the kinetic and the potential energy of an object as its mechanical energy. So capital E could be used to define this mechanical energy. The 3 bars mean that that's a definition. So if we adopt that definition, then our master equation for the conservation of energy could be rewritten in slightly simpler form as E sub I plus the work done by non-conservative forces is equal to E sub F. Okay? And just have to remember, if you write down this as your starting point, you just have to remember that E includes both kinetic and potential energy. One thing about this equation that I'll just mention, don't forget there can be more than one force that has a potential energy function that's acting on the object. We've already talked about potential energy equations for gravitation as well as for spring forces, and there could be a problem where there's an object that is acted upon by both gravity and by a spring. And so if that's the case, this potential energy term on both sides of the equation may have more than one term in it. There might be a potential energy term for gravity and then also a potential energy term for the spring. So be aware that there can be more than one kind of potential energy involved at a given time. So the non-conservative force term in this equation includes the effect potentially of more than one force, but it's any force acting on a given system that cannot be expressed in terms of a potential energy function. And some examples, we've already talked about friction, but air resistance, again, is a kind of a force that acts opposing the motion of an object. That's one that would actually depend on the path the object takes, so that would also be a non-conservative force. And then a tension in a rope. If there's an object that's being pulled on by a rope, it's going to have its kinetic energy increase because of the work done by that tension, but we can't write down a potential energy function for the tension in a rope. So those are examples of non-conservative forces for which we might have to calculate the work done in order to use this conservation of energy equation. So very soon we'll do some examples of solving very interesting problems, and we'll see how useful the principle of conservation of energy is for those kinds of problems. I'll see you in class.